AC electric motor. An alternating current electric motor includes a thin, hollow, cylindrical spool similar to a ring, with mass M equals 1.11 kilograms and radius A equals 5 centimeters, wrapped N is equal to 500 times with a copper wire with resistance R equals 5 ohms and inductance L equals 77 millihenry. Within the spool is a battery that supplies current I 1 amps, which makes the spool a magnetic dipole with dipole moment mu parallel to the cylinder axis. A constant magnetic field with magnitude B is equal to 2 Tesla is supplied by an external stator magnet, while the spool turns freely on an axis perpendicular to its own axis. At a certain time, a bar is inserted, stopping the spool's motion. See the figure. So you can see this spool can rotate about this axis. Because of the current that flows through the coils, we have a magnetic dipole being created here, and this at a certain time makes an angle theta with respect to the externally supplied magnetic field, and there is a bar that's going to stop the motion, so it's going to apply a downward force. At that instant, the angle between the spool axis and the magnetic field is theta equals 45 degrees. Part A, what is the magnitude of the downward force applied by the bar onto the spool immediately after the bar is inserted? So there is a downward force applied by this bar, and therefore this applies a torque with respect to this axis, while the magnetic dipole moment making an angle with respect to the magnetic field feels another torque. Okay, so this is the situation. What is the torque due to the magnetic field? It's mu cross B. So if I have my forefingers of the right hand pointing along mu, curled towards the magnetic field, the thumb points out of the page, which means the torque due to the magnetic field is out of the page. The sense of rotation is counterclockwise. On the other hand, there is this R vector here making a 90-degree angle with respect to the downward force. R cross F using my right hand shows me that the sense of the rotation is clockwise and the torque vector is pointing into the page. So these two torques will balance each other. At equilibrium, we will have the net torque acting on the spool equal to 0. The magnetic torque, tau B, is the cross product of magnetic dipole moment with the magnetic field, which is mu B sine of the angle between them. And looking at my coordinate system here, the way I have defined it, if it is pointing out of the page, that means it is in I hat direction. That's the direction of the torque. And what about the torque due to the downward force? It is R cross F. The perpendicular distance with respect to the rotation axis is R, and the point of application of the force is basically downwards here. So R cross F gives me, because of the 90-degree angle, just the radius A multiplied by the force F, and the torque is in minus I hat direction into the page. So this is F times A in minus I hat direction. That's the net torque we will see. Okay, so working on this net torque is mu B sine theta in I hat direction minus FA in I hat direction, and this must be equal to 0 at equilibrium. So this tells me that the force F, downward force, is mu B sine theta divided by the radius A. Now, what about the magnetic dipole moment? It's the number of turns times the area times the current, the total magnetic dipole moment. So we have capital N terms. Each coil each turn has an area pi a square. So this is the area times, total area times the current. So we have pi a square I due to each coil, and we have capital N coils. So that's the total magnetic dipole moment. Then we have B sine theta divided by A. So you can see that one of the A's will disappear. And therefore, we can write the downward force F as F is equal to capital N. Instead of pi a square, we have pi a I B sine theta. That's the magnitude of the downward force. And if I evaluate this for 500 turns, 500 times pi, the radius is 5 centimeters, 5 times 10 to minus 2 meters. The current is 1 ampere. The magnetic field is 2 Tesla. The angle is 45 degrees. So that gives me a force of, downward force of 111 newtons being applied by the bar that stops the motion of the motor. Okay, so we were asked to find the magnitude of the downward force applied by the bar onto the spool immediately after the bar is inserted. And that's basically the angle, that's when the angle between the spool axis and the magnetic field is 45 degrees. And it is basically stopped. A bar is inserted, stopping the spool's motion. So we're talking about equilibrium. Now part B, later at time t is equal to 0, with spool still at rest, the coil is short-circuited and a constant counter torque of 0.5 Newton meters is applied. Okay, so it is short-circuited at t is equal to 0 after waiting for a long time, and then we have a counter torque being applied. The current subsides and the magnetic torque decreases exponentially. At what time t does the force applied by the bar vanish? The hint is determine the magnetic torque that balances the counter torque. Okay, so what was the counter torque due to? The counter torque was due to the downward force. It was due to the downward force being applied by the bar. If the counter torque balances the magnetic torque, the counter torque applied balances the magnetic torque, it's going to make the downward force vanish. So the downward force vanishes, the counter torque will be enough. So when the coil is short-circuited, we have the following situation. We have an inductor which has a resistance that is basically short-circuited. So we have an RL circuit here. So instead of connecting it to the battery, this is short-circuited. The coil has an equivalent resistance and inductance. So therefore, we have an RL circuit which has a time-dependent current. So in this circuit, if I look at the direction of the current here, the current flows in the direction of dropping voltage, plus minus, plus minus. So potential at R, VR plus VL, should add up to 0. That's Kirchhoff's voltage law. So I can write for this V sub R plus V sub L should be equal to 0. What is the voltage across the resistor? It's its resistance multiplied by the current. What is the voltage across the inductor? It is inductance L di dt, derivative of the current with respect to time. So this must be equal to 0. This means if I isolate the current, di over I is equal to minus capital R over L dt, integrating this from time t equals to 0 to t, from the current value at t is equal to 0, 0 to I of t, one would obtain the natural logarithm of the current, natural logarithm of I of t divided by the current value at I at t is equal to 0, which is the capital I, is equal to minus capital R over L t. So we're integrating from t equals 0 to t, current value at t is equal to 0 to t is equal to t. Okay, so this gives me that the current is going to decay exponentially. Its time t equals to 0 value e to the minus capital R over L t. So that means I'm going to have a magnetic dipole moment that is time dependent. It is capital N pi a squared, the total area multiplied by the number of turns, multiplied by the current I e to the minus capital R over L t. So I have a time dependent magnetic dipole. Therefore, the torque it creates, tau mu, or the magnetic torque, let's call this tau b, is, let's check what did we label this, tau b, yes, so it's tau b, is mu b sine theta, which means this torque is capital N pi a square I b sine theta e to the minus capital R over L t. And this must be equal to the counter torque, tau c. Tau c is the counter torque, such that we don't need this downward force anymore. So that means we can write exponential minus R over LT is equal to the counter torque tau c divided by capital N pi a squared I b sine theta. So solving for time t, we find that the t is equal to minus L over R. We're taking the natural logarithm of both sides. We obtain natural logarithm tau c divided by capital N pi a squared IB sine theta. All right. That's the time it takes to have this counter torque balance the magnetic torque so that there's no more downward force. And if I calculate how much that time is, minus 77 millihenry, 77 times 10 to minus 3, 5 ohms resistance, natural logarithm. The counter torque was given as 0.5 Newton meters, 500 turns, pi, radius 5 times 10 to minus 2 squared, 1 amp, 2 Tesla sine 45 degrees. So this gives us for the current, for the time, 37.1 milliseconds. At t is equal to 37.1 milliseconds, the counter torque balances the torque due to the magnetic field. So when the spool was still at rest, the coil was short-circuited, a constant counter torque was applied, the current subsides and the magnetic torque decreases exponentially, Yes, because we have exponentially decreasing current. At what time does the force applied by the bar vanish? Because we have the counter torque balancing the magnetic torque. So that was the question. So we found that time to be 37.1 milliseconds. Part C. After the spool rotates 180 degrees, it becomes stuck on the top side of the bar. The counter torque is no longer applied and the switch is returned to its original position. After a long time, the bar is removed. What is the angular acceleration of the spool immediately after the bar is removed? The moment of inertia of the spool for an axis along its diameter is 1.2 ma squared. Okay, so if the motor has rotated 180 degrees, so instead of making 45 degrees with respect to the magnetic field, we now make 135 degrees with respect to the magnetic field. Okay, so the circuit is reconnected to the battery, so connected to the battery, and we wait for a long time, which means we recover the original situation. The current now becomes 1 amperes. Okay. The torque due to the magnetic dipole moment interaction with magnetic field is mu b sine theta prime, which is capital N pi a squared I b sine theta prime. The downward force is equal to 0 because we have removed the bar, the stopping bar, and also the counter torque is no longer being applied, which means this is the net torque acting on the system. The net torque is equal to moment of inertia 1/2 ma squared times the angular acceleration alpha. So recall that the net torque, Newton's second law rotational form, is moment of inertia I multiplied by alpha, where I is moment of inertia. So this is not to be confused with the current I. All right, so we can recall this result from our mechanics course. Okay, so that's what we are using here. I note that this theta prime is pi minus theta due to 180 degrees rotation. So I can calculate alpha to be 2 capital N pi. You can see these a squares will cancel. 2 capital N pi IB sine theta prime divided by m. So that will be the angular acceleration of the electric motor. And we can calculate what this alpha will be by substituting the values. Alpha is 2 times 500 turns pi 1 ampere 2 Tesla sine 135 degrees divided by the mass 1.11 kilograms. This gives us an angular acceleration of 4.00 10 to 3 radians per second squared. So that's the answer to part C of the problem. Okay, so in this problem we had this cylindrical structure with capital N turns of coil around it. The radius is A, and when I turn on the current on these coils by connecting the coils to this battery, the current will create a magnetic field in this direction along the axis of the cylinder using the right hand rule, I can see that the magnetic field will be pointing up like this in this picture, and that means there will be a magnetic dipole moment being created, which is the area of each turn multiplied by number of turns, and that magnetic dipole moment is going to interact with the external magnetic field mu cross B, inserting a torque in the counterclockwise sense for counterclockwise sense rotations, or that means the torque is into the page. Now, if I bring another bar that stops this motion, this rotation, by applying a downward force, the torque due to the downward force will balance the torque due to the magnetic field interaction. So mu cross B, mu B sine theta is balanced by R cross F, which is FA in minus I hat direction. From this, I can calculate the magnitude of the downward force applied. Now, if I short circuit the coil and remove it from the battery, I will have a time-dependent current following this circuit here. I can see that this coil is connected to the short circuit, and it has a resistance and inductance. So it's going to have an exponentially decaying current, and so that the magnetic dipole moment will be exponentially decaying, and the torque is mu B sine theta, so that's going to be exponentially decaying. Now, there is a counter torque being applied. Basically, in part B, the coil is short-circuited, a counter torque is applied. The current subsides and the magnetic torque decreases exponentially. As we have seen, the magnetic torque does decrease exponentially due to decrease of the magnetic dipole moment. At what time does the force applied by the bar vanish? That means we don't need the torque due to this downward force anymore, which means the counter torque will be balancing the magnetic torque. The counter torque balancing the magnetic torque occurs at this time t by solving this equation for t. And then in part C of the problem, after the spool rotates 180 degrees, it becomes stuck. So the counter torque is removed. The switch is returned to its original position, and after a long time the bar is removed, which means the current has been restored. What is the angular acceleration of the spool immediately after the bar is removed? Immediately after the bar is removed, the net torque will be due to the magnetic torque. There's no counter torque that's going to balance this magnetic torque anymore. And that magnetic torque is mu B sine theta prime, the new angle between the magnetic field and the magnetic dipole moment, and this must be equal to moment of inertia times alpha, because the net torque is moment of inertia times angular acceleration according to Newton's second law, rotational form. So we can solve for alpha from this equation, and we obtain 4 times 10 to 3 radians per second square as our final answer.